Hello everyone, and thanks for joining me today and another episode of Cyber Llama Talks. And today we're going to talk about machine learning in anti-malware in a period of time 2005 to 2010. And I have to warn you, between 2005 to 2010, there were no ChatGPT or deep learning or any sort of fancy machine learning algorithms which you probably so accustomed nowadays, where they fascinate you pretty much every week something new comes out. But it doesn't mean that machine learning was not in use. It was just different. Approaches which worked back in that period of time were just simply different than approaches which work today. And of course, nowadays, machine learning and deep learning is much more powerful than it used to be. There were still some pretty cool algorithms. And I have to put some asterisk here. It's very difficult to really know what kind of algorithms existed at every single company. So I only have one side of the story, of course, but I'll try to kind of generalize as much as I can and as much as I'm aware of the different algorithms used at that period of time. Well, first of all, machine learning in security has been used before 2005, and I believe one of the most traditional security challenge which people started to solve in machine learning was spam classification, and that was probably beginning of 2000, maybe someone even attempted earlier. But a lot of malware detection using machine learning was influenced by success of spam filters which use machine learning. But I'm going too far. First of all, just for the people who might not work with machine learning on day-to-day basis, when we talk about machine learning, we talk about two types. And the first type is supervised, and the second type is unsupervised. What does it generally mean? Simply put, when we're talking about supervised learning, and let's say we have a binary classification, malware, not malware. Let's say we have a bunch of benign samples, and we have a bunch of malicious samples. And we know labels of benign and malicious. The goal of supervised machine learning is to train the model or generate the model and using both the data and the features and the labels, and they train the model so it can recognize when it's given unknown sample. For example, it gets something like this. We can ask the question, is it benign or malicious, right? And the supervised machine learning has to classify. Unsupervised is different. You might have different categories of the sample in a collection. For example, let's say you have thousands of files in your collection and they don't have a label. And there is no simple way to label them because the reverse engineer and analyze every single sample take a lot of resources and it's just not feasible. And what machine learning tries to help you to answer, let's say if you have a collection of executable files, how many different classes of the files, it can be different benign software, maybe different malware families, you have generally in that collection of files. So you don't have labels. Instead, you're trying to cluster what supervised machine learning very often called clustering, at least in this context, of how many cluster of different files or families we have in our collection. So most of the time when people talk about supervised machine learning for malware classification, the immediate thought come to mind is maybe it's logistic regression, neural networks, and so on. In general, that type of machine learning system, supervised machine learning models, called discriminative. What those type of models try to do, based on the features of each samples, they try to divide all the samples you have into category malicious and benign. So usually, let's say if we talk about logistic regression, you randomly initialize that vector and then you use gradient descent to get closer and closer and closer to that optimal division where you have a best quality of that classification between benign and malicious files. And that type of model is called discriminative. However, there are another type of models which back in 2005, 2010, that was actually one of the most common type of model which we use, and they called generative. And when I say generative, you're like, oh, wait a second, I know about generative. It's ChatGPT and all this awesome generative AI which exists nowadays. And back in 2005 to 2010, that period of time, of course, we don't have that amazing generative system we have right now. However, we did have generative system in general. And one of the most famous one was a naive Bayes. And the idea behind the generative machine learning is, instead of trying to split, when we're talking about binary classification, collection into two classes, let's say benign and malicious, it actually generates the description of both of these classes. And then when you have an unknown sample, it just separately evaluates, is it more probable that that sample falls as a benign or as malicious, based on the generated classes, right? So it works based on probabilities, and every file, based on different characteristics, can be assigned to, let's say, benign class or malicious, based just on probability of the features observed in benign or malicious files before, and these probabilistic models about benign and malicious classes were generated. So a naive Bayes is actually the type of models which were successfully used in the spam classification, and those are also the models which were early on used for malware classification as well. While when we talk about discriminative models, we of course talking about linear regression for classification as well, based on a gradient descent optimization. So those are two types of supervised machine learning. And of course, the most important part of it, okay, what did they use to classify malware? To use machine learning and classify files as malicious or benign, first thing you would need is features. Those early models like linear regression or naive Bayes, they would require a manual feature engineering. And so what does it mean to engineer a feature? Well, let's say the most simplest feature can come from a P header in executable files. When you parse the file, you can have an entry point, number of section, you can compute number of imports, number of exports, and so on. So I call it a primitive. Those kind of features, they're easy to extract, they kind of hard to hide if you're malware. At the same time, they're not very effective. It's almost like searching for this evil bit which would tell you, okay, that's a malware, right? And since it's a very low quality features, they would not generally produce a high quality result, no matter what system you use, and especially they would not produce high quality result using linear regression or naive Bayes. The second type of features we can talk about is a bit more sophisticated. Specifically, it's usually strings extracted from the file, or it's API names. Of course, in early models, we had a very limited computational capacity, and as a result, machine learning couldn't have all the strings possible, all the API names possible exist as the features. And that's why usually when the features are manually engineered, only interesting APIs would be picked as features. For example, maybe create file, nt-create file, maybe URL download file, and so on, right? Probably what would happen is malware analyst or machine learning analyst, there were no such type of job at that point of time, but malware analyst would take thousands of malware samples, extract all the API names, and then take a bunch of benign samples, extract all the API names, and just try to see a top 500 API names observed mostly in malware, but not observed often in benign files. And the same thing would happen with strings. Generally, some strings could be normalized as well, right? Because you can have different lowercase, uppercase, you can have some numbers inside the string, so strings definitely would be normalized as well. These features are not as primitive as the original one. However, they are susceptible for evasion. For example, if sample would be packed, let's say we have polymorphic packer, if you try to extract such features from an original file, you most likely fail. You would need to use emulator or some sort of memory analyzer to extract the memory or unpacked binary after emulation, and then apply feature extraction out of that unpacked binary to extract those type of features. However, the biggest weakness of those strings and let's say API names is they would lack order, right? You might extract a bunch of API names from import table or a bunch of API names from text section, and they would not have any order. It's just a binary feature. It's either API exists or doesn't exist, and you cannot actually see the sequence. And that's the last type of important features which I want to talk about, is sequence-based. Sequence-based features can be very different. It can be, again, sequence of API. It can be sequence of instruction. It can be, well, sequence of API calls. It also can be sequence of API in import table. It's pretty much anything where the sequence or order of those type of features might be important. And of course, how do you represent that type of feature? If entry point, number of section can be presented simply as a number, the existence of the strings or API names can be simply presented as 0, 1, exists or doesn't exist. How do you represent the sequence in the simple models as a naive Bayes or the linear regression? And the way to do it is to present them as one feature. And usually it's called n-gram. What it means is instead of having a feature, let's say create file, you have a feature how often in a file call of create file follows by call of create process, right? And together that sequence is the feature by itself. And in this case, you have 2 APIs, that's 2 gram, right? We can have 3 APIs and so on. The problem, the more elements you have in the sequence, the more combination of different sequences you have, and the more sparse your feature set would look like, because it's less and less probable that the file would have that specific sequence. That's why usually they would use 2 to 3 features in n-gram. And for example, it could be two APIs in the sequence or 3 APIs in the sequence. It could be, for example, type of instructions. For example, what is the sequence of branch changing instructions? You can have GZ, GMP, call inside a function. You can have G and Z, GMP, call. You can have different type, right? So that would be one feature, that would be another feature. And inside the feature vector, it's going to be just presented as, for example, number of occurrences of like that. So, okay, so we build this feature vector, right? That's a number, that's the number, that's a number, that's a number, that's 0, 1, that's 0, 1. And here we have like a lot of numbers which would represent number of occurrences, let's say, of certain sequence of instructions or certain sequence of API calls. And now we're ready to classify. So that's how the classifier would look like. Of course, it will be trained based on a type of the, differently based on the type of model, if it's a linear regression or is it naive Bayes. Of course, neural networks already existed at that point of time. However, the problem at that point were just not enough computational capacity and not enough data for machine learning. There were also attempts to use SVMs and other type of supervised models of classic machine learning. However, I believe in period of time 2005 to 2010, and I might stand corrected, the two most popular algorithms would be a linear regression and a classifier and naive Bayes. That what would be used, and the feature types would be these primitive features, the string-based and the sequence-based features for the classification. Hopefully today's lecture was useful, and now you know more about machine learning and how it was used between 2005 to 2010 in anti-malware or antivirus industry. As always, subscribe, share, give me feedback, and I hope to see you next time.